Okay, good afternoon. Today's last few topics are remaining in our chapter for BJTs. We're going to look at applications, specifically 4 different kinds of applications for a BJT. One in the active, actually 2 of them in the active region, 1 of them in the saturation. And then we'll wrap it up with introduction to logic gates. So we stopped here, where we looked at voltage divider bias circuit for a BJT. All right. Next up is the first application where we take a BJT amplifier and use it to amplify the signal that comes from a diode. In this particular circuit, we are using the diode as a sensor for temperature. Okay, so we're using it as a diode temperature sensor. And the property that we're using for the diode is the variation in the change of the diode voltage as a function of temperature. So if you recall the diode expression for diode current, ID is IS times E raised to VD over VT. So it's inversely proportional to VT, right? As the temperature increases, diode voltage keeps on decreasing. That is what is shown here, okay? The reason for that is as the temperature increases, there are more intrinsically generated carriers, and so the depletion region shrinks just a little bit. And the diode voltage, the voltage that is required to turn on the diode shrinks by about 2 millivolts for every degree C increase in temperature. Okay, so it's inversely proportional. As the temperature increases, diode voltage decreases. This is a very well documented and very well studied feature. The decrease or the increase or any change in the diode voltage is pretty linear with respect to change in the temperature. Okay, so over a range of, let's say, from 0 degrees C to 100 degrees C, the change is linear. And for this reason, many or most of the digital thermometers that we see on the market today use a diode temperature sensor or use a diode at the front end. However, the signal that arises from the diode is very small in current, small in voltage. So it needs to be amplified before it's fed into your digital logic circuit, right? So we connect a BJT at the output of the diode to amplify the signal that is coming from the diode. Okay, so this example is basically about designing an appropriate BJT amplifier to amplify the diode signal or the diode current that's coming through. Okay, now all of this is a very basic rudimentary setup. Okay, there are many other factors that go into biasing a diode and biasing a BJT to operate and account for all environmental conditions. But at its most fundamental level, this is the minimum setup that we need, and you'd be able to actually use this circuit as a sensor. All right. And of course, what is not shown here is the logic circuit that is required to translate change in electrical voltage and current and translate it as temperature. Right? That's a complete separate instrumentation circuit. We are not even talking about that. This is simply the sensing circuit. Okay, so I have marked on the left, I've marked it as the diode, which is a sensor. On the right is the amplifier, but the entire circuit by itself can be referred to as the sensor circuit because the amplifier's function is solely, this BJT amplifier is solely there to amplify the signal that's coming through from the diode. Okay, meaning the voltage and the current that's coming from the diode. So as far as the design goes, we are taking the diode voltage and applying it directly into the base of the transistor. So we have a base resistor RB, and then we need to bias the BJT. So we have a collector resistor RC, and we also need to control the current that is flowing through the diode. So we need a diode resistor, and that is known as, we call this as RS in this example. Okay, RS. Source resistor, series resistor, but it's noted as RS. Okay, so ultimately, we need to determine the values of these 3 resistances. How do we choose the value of the resistor such that, well, first of all, that the BJT is biased in the active region. Again, we want to use it as an amplifier, so it must be biased in the active region, not in cutoff, not in saturation. And secondly, how can we take the diode voltage, diode current, and couple it into the base of the transistor? Okay, so that's RB. And where RS comes into the picture is to control the current that's flowing through the diode. Okay, if you recall from diode characteristics, a p-n junction diode has this sort of characteristic, right? After the diode voltage drop, meaning after the diode turns on, the current increases at an exponential rate. But the slope is very the slope is very steep, but there is a linear-like relationship between the diode voltage and diode current. Okay, so as the current increases, the diode voltage might increase just a little bit, which would be this portion right here. Okay, but the slope is very steep, so we can also treat it as being near constant. All right, and so that's what we will use to determine the value for RS. Okay, the criteria is that the thermometer should be able to function between 0 degrees C and 100 degrees C, which is right here. Okay, how much is it in Fahrenheit? Just as a general knowledge question. 200 something. I heard some murmurings. Is 32F 212. Okay, most of the scientific engineering work is done in degrees Celsius, and imperial units Fahrenheit are used well for everyday usage. Okay, so between 0 degrees C and 100 degrees C is where we want our diode temperature sensor to function, which translates to 32F Fahrenheit and 212 Fahrenheit. All right, so if you wish to be somewhere in the center, we want to bias our VCE output somewhere in the middle or halfway between our chosen VCC. So we would take VCEQ, meaning our Q point for the BJT, and position it somewhere in the middle between 0 and VCC. If we use VCC as 12 volts, we choose VCEQ for 6 volts. If VCC is 10 volts, we choose VCEQ approximately 5 volts. Okay. Most handheld digital thermometers run either on one AAA battery or 2 coin cells. So it's either 1.5 volts or it's 3 volts. Okay, so that would be your VCC that you're applying into your circuit. But again, as an example, let's just choose like 12 volts. So if we choose VCC as 12 volts for our circuit, then VCEQ halfway between there would be approximately 6 volts. Right? So we begin there. We are working backwards. Right? So our output voltage VCEQ is about 6 volts. And then the next point is that we want to hold the diode current nearly constant. Okay. If you want to hold it nearly constant, that means that VCC should be far larger than our diode voltage. So if you look at the circuit, this current is flowing down here, right? Some of it will go through the base. Most of it should go through the diode, right? So IS is equal to ID plus IB. If you apply KCL at the base, let me bring it down here. I would say total current coming from the top, IS, is equal to ID plus IB. Now, IB is going to be very small, right? We want to keep it very small. So we could treat it, potentially we could treat it as negligible. And so we can say IS is approximately equal to diode current ID. So the current flowing through the resistor RS would be very close in value to the current flowing through the diode ID. Okay. And RS is connected between VCC and diode voltage VD. So the current IS can be described as VCC minus VD. So VCC minus VD, because it's between these 2 points, divided by RS. And in order for IS to remain approximately constant, we need VCC to be far larger or far greater than diode voltage VD. And so we can describe IS, and I have it down there, but I'm just going to write it here, VCC minus VD or RS. Okay, VCC minus VD or RS. And we will use this equation to determine the value for RS. Okay, now IB is the base current that is going into the transistor, BJT. Our decision or our design requires that we bias it in the active mode. If we bias it in the active mode, then the base voltage is VBE is 0.7, right? It's 0.7. So if we choose that, we can describe the current IB as VD, diode voltage minus VBE or RB. Now, for all intents and purposes, the diode voltage would be almost equal to VBE, depending on minor differences, of course, on the construction of the diode and the construction of the BJT. We would want the diode voltage to be higher than VBE. So when we are choosing component values, we want the current to flow into the base and not out, right? So we want diode voltage VD to be higher than VBE, but not by much. And so when we design it, we choose our components such that diode voltage, the difference between the diode voltage VD and the base emitter voltage VBE is about 0.01 volts, very, very small. And if we do that, then we can say IS, IB is very small, so IS is equal to ID. And we can choose diode current ID to be about 100 milliamps. Again, this is all about designing, right? As an engineer, if you're designing a new system, you would make certain assumptions and you would start picking certain values based on your application, right? And then you would test out your system, see if it works. If it doesn't work, you go back to the drawing board, you change one variable and you try it again. So there are multiple iterations, right? You have to keep redoing analysis on your system until it's, until it works within specification. So we begin by choosing ID as 100 milliamps. ID is 100 milliamps. At 50 degrees C, VD is approximately 0.8. This is approximately 0.8 or 0.78. We are just choosing 0.8 for convenience, calculation convenience. And then I can calculate RS as VCC minus VD or IS, which is 100 milliamps. And so I calculate RS as equal to 112 ohms. Okay, 112 ohms. Now, when we talk about design, we always are talking about real world values, right? We are talking about real world values for these components. So real world, we won't have a resistor of 112 ohms available. We have 100, 120, and so those are the closest values. So if we choose 120, then our current will be less than 100 milliamps. which would cause issues, right? So we don't want that. So we'll choose the lower resistor value so that current is larger than our desired current. We can go larger, but we should not be going lower. If we go lower, then the diode voltage will drop. If the diode voltage drops, then the base current will not flow into the base. It will actually flow out. So we don't want that. So we choose a lower value for the resistor, which is 100 ohms. Keep the current large. When the current is large, sorry, not current. When IS is large, then IB will flow into the base. All right. So if we choose RS as 100 ohms, we can also choose RB to be very close in value. Again, we pick the same value, simulate the circuit, see if it works. If it doesn't work, then we can go back and change it. But for convenience sake, we can choose RB to be the same as RS and 100 ohms. Okay. So RB and RS will both be at 100. And then lastly, we want RC. So if you want to find RC, we go over to the output side, apply KVL. On the output side, we only have these voltages, VCE and ICRC. So VCC minus ICRC minus VCE is equal to 0. We already have value for IC because we are using IB, we're keeping it very small. So if we assume that VD minus VBE is kept to 0.01, again, VD is slightly higher than VBE, we keep it to 0.01 and RB is 100 ohms, we can keep IB to be approximately equal to 100 microamps. Very small value. And with that value of IB, we can get IC as approximately equal to 17 milliamps. Okay, 17 milliamps. And from there, we can calculate RC as 353. Okay, 353. Yes. Approximately. Yeah. We can choose 6. Actually, we talked about 6, right? But we are just looking at the parameters of the BJT. So the question being asked is, why are we choosing VC at 6.5? Good question. So we looked at the spec sheet for a specific transistor. I believe this was 3904. Yeah, 3904 right here. And so the temperature dependence of the 3904 is that around 50 degrees C, which is our midpoint of the measurement range, is approximately equal to 6.5 volts. Okay, so that's why we are choosing that, which is right here. Approximately 6.5 volts. Now, if you recall the last circuit from the last class, previous class, we talked about voltage divider bias. The reason we use the 4 resistor bias is to make that transistor configuration independent of the transistor beta, which may not be possible here. With this simplest of circuits, this transistor would depend on beta. So if you take right now, the beta value that's being used is, let's see, I thought I had it in here. I think it was about 35, 40. I think it's 40, according to the spec sheet. So the transistor changes, the beta value changes, and instead of being in the active region, your IC would be larger and it would drive the transistor into saturation. Again, we are using one specific value for IB and one specific value for IC. Okay. So if we change the transistor, use the same model, 3904, but the beta is quite large, larger than the 40 that we are using in this circuit or for this analysis. If it goes to like 75 or 80 or 100, then our IC is large. If IC is large, then VC goes into saturation. BJT goes into saturation. It's no longer working as an amplifier. It's not in the active region anymore. So then this circuit would not work. Does everybody understand the point? Right? But most diode-based thermometers use some variation of this circuit. You have a diode in there, right at the sensor tip, and then the diode voltage changes as a function of temperature. That change is very well documented, and it's linear as a function of the temperature. And the output, meaning the diode voltage, is fed as input into an amplifier. In this case, it's a single BJT amplifier, so into the base of that amplifier. All right, questions? Not an easy circuit. Even if you ask your EE friends or peers to explain this, they'd be hard pressed to do so. Even me. Every circuit is different, and so it takes a while. Okay. The steps do not change. Okay. Still circuit analysis techniques. We are applying KVL at the output. We have KCL on the input side. The application of techniques will just change depending on what we are trying to accomplish. Okay. So this was the active region. Here, if you want to use it to drive an LED, then we want to use it in the saturation region or in the cutoff region. So we are using it as a switch, not in the active region. Okay. So oftentimes you might have a sensor, you might have a microcontroller, you might have a system, and the output of that system is low voltage and or low current. And that would not be enough or sufficient enough to drive either a motor or to drive an LED. So in this first application, there's an LED. After this, there is a battery charger and a DC motor. Okay. So let's say this is the output of a sensor or microcontroller right up top, right here. Okay. The mu C is not microcoulombs, it's just the author's notation for a microcontroller. Okay. So let's say there's an output of a sensor or a microcontroller, and every time a event occurs, a light is supposed to flash, as in that something has happened, right? And you see this in systems all the time. You might have a, I don't know, like a toaster or an oven. When it's preheating or it's done, light pops on. Now it's ready. One could be a green light, one could be a red light. Could be a simple circuit, could be a involved circuit like an LED with a BJT driver, okay? But nevertheless, many systems are out there where we need to have a visual indicator that an event occurred. And in that case, we connect a simple BJT, and this BJT is operating either in cutoff or saturation mode. If it's in cutoff mode, there is no pathway for the current to flow through. If it's in saturation mode, there is free and clear pathway for the current to flow through. So the circuit is set up like this. There's an LED, right? There's an LED, and it is connected to a switch. It's connected to ground. You're applying plus 5 volts to that LED via a switch. If it's a push button switch, you push the button, turns on, right? But in this case, it's not a manual push button. We are using a digital switch, which is the function that the BJT is performing. And so you have the input that's coming from your sensor, and that is going to activate the switch. That's all that equivalent circuit is. You have an LED, you're supplying power to that switch. It's like a flashlight. You have a manual button, except the manual switch is a BJT. And the BJT is activated by a signal going into its base. The signal may be coming from a microcontroller, from a system, or a sensor of some sort. Okay. And so this would be your input. And this is the digital switch. BJT in cutoff. Switch is off. If BJT is in saturation, we say the switch is on. Okay, so previous application was in the active mode. This is in cutoff and saturation. All right, the voltage to turn on the LED is approximately 1.3 to 1.4 volts. There are some LEDs you can turn on at 1.1 volt. The current in the light will be very dim. To have full brightness, it might require anywhere between 20 to 30 milliamps of current. And so those are the specifications that are from the LED itself. And the maximum power dissipation in the LED is 100 milliwatts. Okay. LEDs do not get as hot as our incandescent filament light bulbs, but they still dissipate heat. Okay. It's still an electronic device. There's still a PN junction. So most of the energy is dissipated as light or photons, but there's still a substantial portion where it dissipates as thermal energy. So we always have to care about the power rating, 100 milliwatts in this case, okay? Beta for the transistor is about 95. Sensor output is digital output going from 0 to 5 volts, okay? So let's say, again, taking the example from the lab, turnstile, like a switch, right? So one person walks to the turnstile, sensor goes from 0 to 5 volts and then goes back to 0. Every time it goes from 0 to 5 volts, the BJT is now driven into saturation. When it drives into saturation, LED has a clear pathway, turns on. So the chain of events goes that a person walks to a turnstile, activates the sensor connects the output to plus 5 volts, goes back down. So you have one pulse going from 0 to 5, goes back to 0. That is fed into the BJT, which is driven into saturation, which turns the LED on. Person walks in, light flashes. How many times have we seen that? Right? Many times. We do it without thinking, but there's a lot of things that go on behind the scenes. Okay, so in saturation mode, if you wish to model a BJT, VCE SAT, 0.2 volts, constant voltage source, right? And that's what we see here. So a large signal model for a BJT in saturation, if you recall, was a simple voltage source of 0.2 volts. LED, once it's on, can be represented again by its diode voltage drop, which is 1.4 volts, right? Once it's on, transistors and BJT as well as the LED, it's going to cause a drop of 1.4 and 0.2. And you have current flowing through the circuit. And so in this case, if you apply KVL on the output side, you obtain VCC, which is divided across three components, VCC minus the LED voltage, VLED, minus the ICRC voltage drop, and minus VC SAT. Should sum up to 0. Now, in this case, our design parameter is that we want to determine the value for RC. Okay. So let's choose VCC as 5 volts. Therefore, ICRC drop would be about 3.4 volts, right? 1.2, 1.4 for the LED, 0.2 for the transistor. So ICRC drop is 3.4 volts. We know that the collector current should be 30 milliamps, which is what the LED current is. And therefore, we can calculate RC from that equation, which is 113.33 ohms. Again, this is not a real life value. This is simply the theoretical design. A real life practical design, the closest resistor would be 100 ohms or 120 ohms, right? Again, 100 or 120. If we choose 120, our current would be slightly less than 30 milliamps. So probably best to choose something smaller. Okay, so we choose 100 ohm resistor. Now, in this particular BJT operation, we want the reverse. We want it to stay in saturation. In the previous circuit, we wanted it to remain in the active region. Here, we want it to remain in the saturation region. We don't want it to leave the saturation. Saturation means current is at a saturated constant level, right? The flat horizontal line. So we don't want it to leave that region. We don't want it going back into the active region. And so to ensure that it remains in the saturation region, which means IC must be large, which means IB must be large. And to ensure that IB, the base current, remains large, we choose RB with an appropriate value. Let's test out. If we choose IB as 1 kilo ohm, if we choose IB, our base resistor as 1 kilo ohm, I'll bring up the circuit again. Then, then I can calculate IB from this equation. RB is connected between the output of the sensor and the voltage drop, VBE. In this case, referred to as V gamma. Again, IB is the current that's going into the base. RB is connected between these 2 points. One end of RB is coming from the sensor, which is plus 5 volts. The other end is VBE, which is V gamma, which in this case is specified as, I believe it was specified at 0.6 or 0.7. And so we calculate IB. So IB turns out to be 4.3 milliamps. Typically, the base resistors were kept large, like in kilo ohms, so that the base current would be in microamps. But this time, we want the base current to be large. So 4.3 is a large value. 4.3 milliamps is a large value. And that would always mean that the current ratio for IC and IB is going to be far less than the transistor beta. We could replace this transistor with a different transistor with a different kind of beta. The beta of any transistor would not be less than 20 or 30. Okay, so this design, this value of RB, which is 1K, 1 kilo ohm, will always keep IB large enough to drive the transistor into saturation. And we want the transistor to remain in saturation, not to come out and go into the active region. Okay, once it goes into saturation, it behaves like a constant current source. It is flowing through, and it allows a pathway for the LED current to flow through. So it turns on and it flows through. When the sensor signal drops from 5 volts to 0 volts, there is no more base current. If there is no more base current, base emitter junction is off, transistor is cut off. There is no pathway for the LED, so the LED is completely cut off. All right, let's take a pause. Let me know if you have any questions. Again, there's a lot to think about, so I'm sure once it sinks in, you'll have plenty of questions. But I have about 15 minutes left, and I have 3 more slides to cover, so I'm going to move on. Battery charger works in about a similar way. We want the current to flow through the battery. We want to provide a pathway for the battery. And once it reaches full charge, we should want it to shut off, right? And so circuit seems very similar, but the explanation is slightly different. Okay. Based on the amount of current we want to flow through here, we can choose the value of the resistance that's going into the base. So these resistors, R1 and R2, are connected in series. R2 is a variable resistor. right? Variable resistors, also known as potentiometers, 3-terminal resistors. The outer 2 terminals are fixed. The middle terminal can be varied, either a linear or a rotary dial. And so we vary or change the value of the base resistor. In this case, we are trying to charge a 9-volt lithium-ion battery. So our VCC, total supply voltage, must be larger than 9 volts. That's pretty much a given. Right? Your supply voltage must be larger than your battery voltage. Otherwise, the battery is not going to charge. So VCC must be greater than 9 volts. Let's choose VCC as 12 volts and begin from there. So if we choose VCC of 12 volts, no matter what VCC we choose, okay, a transistor is not going to be in saturation. For a transistor to be in saturation, your VCE sat, meaning the output of the collector, would be about 0.2 volts. Again, your battery is directly connected to the collector, right? So if the transistor is in saturation, VCE, voltage at the collector, would be about 0.2 volts. So your VCC to keep the transistor in saturation would be 9.2 volts, which means practically your circuit may not work. Okay, VCC should be far larger. Typically for a 9-volt battery, I would choose at least 15 volts or larger. Okay, so if we choose 12 volts, what is our VCE? VCE is 3 volts. That means transistor is not in saturation. Okay, it's not in saturation, so it must be either in the active or the cutoff mode. But if it's cut off, then there is no pathway for current to flow through. Nothing is happening. So the only mode remaining, only choice we have, is that the transistor must operate in the active region. So transistor operates in the active region, in the active mode, meaning IC is a function of IB, beta IB. Okay. All right. So if we start on the left, again, similar techniques we are simply applying, and the explanation is a little different, but techniques remain the same. IB is applied to the base. So from there, we can calculate the values for RB and IC. So in this equation, we have VCC minus V gamma. But the base resistor now comprises of R1 and R2. Right? R1 and R2. And R2 is the variable resistor. We can change what R2 is. So this R2 can be 0 or the max value. Right? When alpha is 0, meaning the slider is all the way to the right, R2 value is 0 because it short circuits R2. Look at the image later. But if this arrow is all the way to the right, then it bypasses R2 completely. Okay, so that's known as the multiplier. So alpha is equal to 1 on the left, alpha is equal to 0 on the far right. Okay. So if the circuit all right. So when alpha is equal to 0, R2 is equal to 0, we get IC maximum value. Now, IC specification is given that can vary only between 10 milliamps and 100 milliamps. Okay, 10, sorry, not 10 and 100. Let's go at the top. Oh yeah, 10 and 100 right here. IC can vary only between 10 milliamps and 100 milliamps. Okay, otherwise you're going to end up blowing out your battery. So maximum value for collector current IC is 100 milliamps. Minimum value is 10 milliamps. And so when R2 is 0, we get IC max. Lowest resistance gives us the maximum current. 100 milliamps, we plug that in and you obtain R1 value as 11.4 kilo ohms. Okay, 11.4 kilo ohms. Now that we have the R1 value, we can use the similar equation to calculate the R2 value. Okay, now we go to R2 as R2 max. So maximum value of R2 would give us the minimum value of the collector current, which is 10 milliamps. We plug that in and we can calculate the maximum value of R2 max, which is 102.6 kilo ohms. Now, obviously, this is not an automated charger, meaning it's not going to shut itself off, right? So again, this is simply to show how a transistor can be used to control the current that's flowing through your battery so you can charge it up, okay? Your battery can be charged just as a separate point. Have you ever had your batteries or rechargeable batteries drop below certain levels? They don't charge up again. That happened, right? Here's a trick, which don't do it with college equipment, but here's a trick. You can take your rechargeable battery and directly connect it to a power source, not the AC power outlet. I'm just saying like a DC source, whether it's if it's a 1.5 volt battery, rechargeable battery, it's not charging up, connect it to another source of like, let's say 3 volts DC and try to raise it level just for a few minutes. Hopefully, it will impart just enough energy from those few minutes that it raises level and you can plug it back into your charger and start charging it. I've done that before. I've also done some crazy things with alkaline batteries, but that's not that's not a fit topic. All right. Lastly, its application is motor driver. This is an interesting application. We want a really large current flowing through our motor for our application, right? So we have the motor current IM, which varies from 0.11 amp, means 0.11 amp is 110 milliamps is required to turn it on, and the maximum current is 2000 milliamps, okay? So a really large amount of current. 2 amps is, by the way, is a really large amount of current, okay? It dissipates a lot of heat. If you look at your battery chargers, your USB chargers, they used to be just 1 amp when they first came out 15, 20 years ago. Actually, it was like 500 milliamps, which is still the standard spec for the USB ports in our laptops and our computers. Fast chargers simply increase the level of current, okay? So in this motor, we need a large amount of current to flow through, which cannot be handled maybe just by a single transistor. So we take the previous circuit and we drive the output into the base of another higher power transistor. And that transistor is able to support 2000 milliamps or 2 amps of current, okay? So there are some equations that relate both transistors. It's basically the output of one transistor, IC1 is equal to IB2, okay? IC1 is equal to IB2. Sorry, not IC. IE1, the output is taken from the emitter. So IE1 goes as base input of the second transistor, okay? And so go through this calculation, the analysis. All we're trying to do is find the value for the resistance and for the R2 max that we saw in the previous circuit. So the first half of the circuit is exactly the same as the previous one, the battery charger circuit. The second half is simply a regular BJT that allows the motor current to flow through itself, right? 2000 milliamps. Okay, and 5 minutes left. Gates and switches. Rudimentary gate. What kind of gate do you think this is? Are you sure? Someone was very quick. They did their reading. Let's use ideal diode analysis. What's the truth table for an OR gate? You give 0, 0, you get 0. You get 0, 1, you get 1. 1, 0, 1, 1, 1, also 1. That's a truth table, right? OR gate means logic OR means mathematical summation. 0 plus 0 gives you 0. So even if a single input is high, the output is high. I like repeating that statement. Output is high. If, oh, actually, this should be connected like this, and this remains off. Okay, and this is your V out, VO. So if I'm ignoring 0, 0, because if it's 0, 0, then both diodes are off, output is 0, right? Because its V out is connected directly to R. But let's take the case where one of the diodes is connected, and it's given the input plus 5 volts. So the diode turns on. When the diode turns on, behaves like a short circuit. So you're giving 1 and 0 because it's right. Then V out is connected to plus 5 volts. So V out is equal to 1. And we saw the implementation of this as an AND gate. Same configuration, but what was the difference? Flip what? The diodes? Not quite. Some of you did the lab today, didn't you? We didn't flip the diodes. No, just the resistor. Oh, that's right. On this one. Brain fart moment. I'm sorry. You are right. I'm wrong. We had a pull-up resistor and we flipped the diode. But what if we don't flip the diode? What kind of gate do we get? So if we have this and we simply connect it to a pull-up resistor, what did we get? You get a 1 at the output. You get a 1 at the output. But, and I think I'm almost out of time. Darn it. Okay, I'll leave this for now. Let's one final circuit. We can also create some sort of like NAND gates with this. So I'll write it up separately. But we saw how we can use BJT as a switch, right? We saw BJT as a switch. It, in fact, is a rudimentary or the most basic inverter circuit. If we give if Vin is equal to 0, what mode are we using the transistor? Or what mode are we biasing? If Vin is equal, there's no input based current. It's cut off. BJT is off. So what is my output? VO. VO is directly connected to plus 5 volts. So VO is plus 5 volts. So if Vin is 0, output is plus 5 volts, meaning logic 0, output is logic high, inverted output. If Vin is turned on, meaning plus 5 volts, or any other level, let's say, logic high, BJT turns on, what happens to VCE? Drives it into saturation. VCE sat 0.2 volts. And 0.2 volts is considered to be logic low. So logic 1 and logic 0. Okay, so most rudimentary or the most basic, most fundamental circuit for an inverter is a simple BJT operated either in cutoff and saturation mode. It's an inverter circuit. All right. Okay, so we'll end class here today. Please review these slides and let me know if you have any questions. You had to rush through the last 3 classes to just get caught up on. So from Friday until the end of the quarter, we are going to work with FETs and logic gates.